more enjoyable than a regular school day because everything was interactive.
Okay.
So you got to talk a lot with your peers and stuff like that, which made it a little more interactive and more enjoyable than a regular school day where you just sit.
Kind of like what we're about to do today.
Yeah, but like all my other classes are like that too on days like today, so it's like competitive. Yeah.
Today will be a lot of writing here, but then the next few days will be practice and stuff like that. All right, guys, go ahead and get your packets out. We are on the comparing two means or difference of means section today, so go ahead and find this in your notes. Go ahead and put those phones away, guys. Like still sitting on your lap isn't quite away.
I
see some people still digging for their packets. You have your... I didn't see it. Do you need extra ones? I think I have one more. All right, guys, so again, we're going to look at how this compares to the one sample stuff that you already know. So for a percentage. So for one sample. Remember this mu of x bar was equal to mu. So when we're doing the difference of means, we just have these two x bars we're subtracting, and then again the equal sign got lost here. So mu of x bar 1 minus x bar 2, that's the same as mu 1 minus mu 2. Okay? So again, just like with proportions, it's very, very similar. You just have two populations that you're dealing with instead of one. Okay? Our standard deviation, when we had one sample, remember sigma of x bar? That was equal to sigma over square root of n.
I did a test.
Video's up. So you can go back and watch day one. All right, so now again, when we find the standard deviation, when we have the difference, we cannot actually add standard deviations, but we can add variances. So that's why the formula is the square root of our sigma squared. Okay? Remember, variance is just standard deviation squared. Yes? Okay. Math note, I think you guys know this, but let's make sure. If I have the square root of 9 plus the square root of 4, is that equal to the square root of 9 plus the square root of 4? No. Okay, just making sure we understand how that works. We know square root. Okay, so let's look at just this little example that's in here. So the AP test has two parts, each normally distributed. Part 1's normal with your mean of 25, standard deviation of 6. Part 2, mean of 20, standard deviation of 7. And then we're going to describe the total score of Part 1 and Part 2 combined. So you can actually add your mean. So if I wanted to do mu of Part 1 plus Part 2, that would just be the mu of Part 1 plus the mu of Part 2, which is what, 25 plus 20? Or 45. But if I wanted to do the standard deviation of that combination, squeeze it in right here, I can't just do 6 plus 7. Okay, you have to actually do the formula. So it'd be 6 squared, and it's over 1 because we don't actually have a sample size here. We're just looking at the sample, and then plus 7 squared over 1. And so we get, what's that, square root of 85? 9 point something. Is that like 9.2? Yep, trusting me to do that. Does that give you the idea of what you're doing with the formula? Okay, squaring them, adding them together. Yeah. 6 squared and 7 squared. And that's just from right here.
Oh, the standard deviation.
Yeah, just the standard deviation squared. Now that was combining the two parts. You're not really going to do that. You're going to look at the differences between two things when we go through this, but that's just showing you how the formula works. Okay. All right, now that was all if sigma was known. If sigma's unknown, what do we do? Because remember this with our one sample, then we were finding standard error, which was just s over square root of n. So if we don't know sigma, we have to use s. So again, we're squaring, we're looking at the variances and adding those together of the two populations. Degrees of freedom, I'll show you just, two ways to do it. You can do it on your calculator, or you can just use the smaller of the two population sizes for your n minus 1. Okay, it's slightly different, but that's the easiest way to go. Our conditions before we checked for normality. We could do that with the population being normal. We could do it with the central limit theorem if n was greater than or equal to 30. Or you could do the normal probability plot is approximately linear. Remember all of those ways? And then we wanted to look for a simple random sample. So the only thing we are adding is that our samples are actually independent of one another. We are still not going to look at that 10% rule. It never shows up on a free response scoring rubric, so we're not going to worry about it. Okay. Questions so far? All right, turn the page when you're ready. All right, and now we have all these different processes, our confidence intervals and our hypothesis tests. So what we were doing before was one population. When we did a confidence interval, that was called a one sample Z interval for means. So now we're just looking at a two sample Z interval for means. And our formula before, remember, was just x bar plus or minus Z crit times sigma over square root of n. So when you look at our new formula, we aren't just talking about a single population here. We're looking at two of them and we're comparing them. So instead of just x bar, it's the difference between my two x bars. Okay, we've got our two samples happening. Z crit is the same. Nothing has changed with how you find that or how that works. And then again, this, instead of just the standard deviation, it's our new standard deviation formula. Okay? Very similar. Then we have our tests, our hypothesis tests. Before we had the one sample Z test for means. Now we have a two sample Z test for means. And again, we're looking at sigma known since we're dealing with Z. You know your Z formula from before, x bar minus mu over sigma over square root of n. You guys see how it relates? just subtracting 2 of them now because you're talking about 2 different sample means and populations. Okay. As we're getting more and more of these tests and confidence intervals, do you guys see why it matters that you write the name of what you're doing? Okay, that's in every grading rubric is was the test name specified. So please get in the habit of doing that. Okay. Then we have our confidence interval when we do not know sigma. So sigma unknown. Before we called that a 1 sample t interval for means. X bar plus or minus t crit times s over square root of n. So the general rules of when you're doing a z, when you're doing a t, none of that has changed. You're just identifying whether you're looking at 1 sample or 2 samples. Okay, and the process is very similar too. Then the last one, if we are doing a t-test, we had a 1 sample t-test. Means t was x bar minus mu over s over square root of n. And very similar. Questions so far? I know we haven't really done much yet, so. Anybody, anything? No, what do you got? Well, and you have the formula sheet. Do you guys want a formula sheet while we're looking at all of this, just so you can see what's on there? Just so you're...
What do you think? You feeling good? Yeah, play your game. Yeah. Play your game. And if not, I'll come in and play you. Sorry.
No, does that make you feel better? Open it. Yeah. Yeah, I didn't staple them. I don't know what happens to some of them, but it's all the same pages, just stapled weird. All right, guys, when you're ready, let's turn the page to our matched pairs t-test. So guys, it's a t-test. What do you think that means? Okay. And then matched pairs is a very specific type of t-test. So you use it a lot for, I mean, these are the most common ones, like if you have 2 very similar people and you want to test something on them, like sets of twins work well for matched pairs, or any sort of before and after is going to be a matched pairs t-test. It's something where you care about the difference of the 2 results at the end and looking at that total difference for every subject in your test. And I'll show you an example. We'll go through one today. And then these are, these are just a couple more examples. The thing that's different is how we write the mu. We write it with a delta. So matched pairs is the only time we use that little delta. So we are not going to write like mu1 minus mu2. It's always mu delta, meaning the average of the difference of the change in your two sets of data points. Okay? And that's basically what it's saying. Same thing, standard deviation. You see the little delta in there, okay? Always n minus 1 for your degrees of freedom of the smaller sample size. Conditions, same as we were doing before, okay? So part of the challenge that is happening now, you're getting better at just the general idea of hypothesis testing and confidence intervals because you're now doing it for a whole other unit. But you have to identify which one you're actually doing. You have more choices now, okay? So let's practice some. All right, so we did our proportion stuff. So let's find this one. This is our first means problem. Okay, so first thing we want to do is define the two populations that we're looking at here. So what do you think we're talking about here? A minute to read. What are our two groups? Boys and girls. And what do we care about within those two groups? Height. So I'm going to define P sub B as the proportion of, we're looking at Madison ones, right? I want proportion, I want average, sorry guys. Let's start over. Why am I doing P if it's a means problem? How about U of B? Okay, the mean height of JMHS boys. And then mu sub G, what do you think that's going to be? Yeah. Guys, this is a step that's easy to forget, but please don't. This is, it's like 3 points in your free response questions, okay? You don't have to have any idea how to do the problem. You just have to tell me who are we looking at? What do we care about, okay? And then let's write down what we know. Do we know mu sub B? Do we know the average of boys in JMHS, their height? Yeah, what is it? 67. Do we know sigma of B? Yes, it is 3, right? And then do we know our sample size for boys? All right, then we should have all that same information, but for girls. So the average was 65 inches. Our standard deviation for girls was also 3, but our sample size for girls was, what, 15? Okay. We've done nothing yet with the last line in the problem here, asking about if boys are at least 3 inches taller than girls. That's going to come into play later. First, we're just writing down everything we know, okay? What do I need to do for both of these populations? Conditions, yes. So, conditions. Normality, it was stated, right? Population was normal. What about SRS? that stated?
Yes.
What do you think? Are my two samples independent of one another? Yeah, you're not going to be included in both groups for average here. Okay. So independent. Yes. Do you have to rewrite all of that for the girls? Yes. You do. Okay. So far, so good? Okay. I'm just going to jot down at the top here what we're looking at. We are looking at the average difference of the heights of boys and girls, right? So I'm looking for mu of P minus G. So this is the difference. Okay. I feel like I'm going to run out of room. Okay, so do we know what mu of B minus G should equal? That's just mu of B minus mu of G, right? So that's going to be 67 minus 65, which is 2. All right. Then I want sigma of boys minus girls. So that's going to be square root of sigma of boys squared over sample size for boys plus sigma of girls squared over sample size of girls. I don't know that you can tell a difference between my B's and G's there. Boys first and then girls. Okay. So in this problem, that's 3 squared over 10 plus 3 squared over 15. And I think it's about 1.225. Everybody a chance to catch up, and then let's look at what we're actually talking about. All right, so if I haven't standardized anything, let me just make a little sketch here, and then I'm probably going to make a different one with standardized values. Right now, we are saying that the difference of these average heights here is 2, right? That was mu of boys minus girl heights, okay? And the question says, what's the probability that the boys are at least 3 inches taller than the girls? So 3 is over here, right? And at least that would be 3 and above. You're with me there. Okay. So let's find our z-score for 3. How am I going to do that? Well, let's find z first, and then we'll do norm CDF once we have z. Okay? You could do it from here. Showing that you know how to find z is not a bad thing. The z is going to be on your formula sheet, which is nice. So I'm looking at the average here of boys minus girls minus the mu of boy minus girl over sigma of boy minus girl. Okay? This is the piece that I think you guys sometimes aren't sure where it comes from. Because we don't actually have like, oh, the sample of boys gave me this X bar and the sample of girls gave me this X bar. That's fine. We have it in here. What are we saying? We're talking about the difference being 3 or more, right? So the 3 is what goes here, minus the 2 was actually the mu, the difference in the populations there. Okay, and then this is our 1.225. So my z is 3 minus 2 over 1.225, which comes out to be about 0.207. Oh, I lied. How about 0.816? Is that better? What do I do with that then? Yeah, because what I'm really talking about is if this is standardized at 0 and my z-score is 0.816, what's the area in there? How do I find area under my curve? Norm CDF. So I'm going to do my norm CDF from 0.816 to infinity. And since I've standardized it, I'm using 0 and 1.225. Since you've standardized it, you don't have to label those two little pieces, okay? And I should get about 0.207. Yes. 1 point. No, we standardized it, so it should be 1, right? I don't trust myself. Yeah, it's 1. So the other way you could have done it, if you didn't find the z-score, if you did your norm CDF and you did 3 to infinity, 2 as your mean and 1.225 as your sigma, and you would get the exact same answer. So guys, it's okay if you want to do it that way, you just have to label everything. Does that make sense? Because I know we've done it both ways in the past too, so that's not any different. Okay. Clearly I'm combining my ways here. All right. We have to write what this actually means. So do you guys have any idea what that 0.207 is telling us? Probability of what? The what? I'm sorry. Yeah, and what's it? Like, what are we talking about? Yeah, okay. So I don't have enough room. Hopefully you guys do. So this is what your conclusion would actually be. There's about
I got the right answer.
a 20.7% chance of boys at JMHS being at least 3 inches taller than girls in JMHS on average. Okay, you've got to include that on average at the end here, because it's the average difference that we're talking about. Okay, so on average, this is how likely this is to happen. Okay, how do we feel? All right, Kyle. Questions on any part of that? Okay. And guys, I didn't write the name of this because this one was just a sampling distribution problem. Okay, it's not actually a hypothesis test or a confidence interval. But our next one is a two-sample t-interval for means. So when you get to the test, I'm not going to tell you, hey, it's a two-sample t-interval. Okay, you have to be able to figure that part out. This is what you need to write when you're telling me what test you're doing, whether it's a confidence interval or a hypothesis test. Okay. All right. Give you a second to read. All right, so we're still looking at heights, but now we are looking at Langley. I'm going to squeeze in some of my info over here on the left. What do you think mu of b is? Well, what do we have to do first? So let's go back. Remember up here how we did all of this stuff? This is where you need to start, guys. Okay? On a free response question like this that's worth 4 points, only 1 point is actually this work down here finding what the percentage is under here. 1 point is usually the conclusion, and then 2 of the points come from identifying this information, checking your conditions, telling me what the test is. Okay, so you cannot skip this step. All right? It's the freebie. It's annoying, I know. It takes a while to write it all, but do it. It matters. So, what is mu of b in this problem? Yes. Mean height of Langley High School boys. Okay, this time, do we know mu of b? Do we know the actual mean of the population? No, we do not. Do we know sigma of b? No, that's why it's a t-interval, okay? Do we know x bar of b? Yes, 66.9 inches, right? All right, do we know standard deviation of the sample for B? Yes, what, 3.08? And sample size for boys was what, 55? You're okay with that? It's the one other thing I need to do for the boys section here before I move on to the girls. Conditions, okay? All right, conditions. Normality, how are we going to check that? What is it? Yeah, what is our sample size? 55 is definitely greater than or equal to 30, right? That's that central limit there. Let's see, was it a simple random sample? Yes, that was stated, random sample. Are these samples independent? Yes. Okay. Okay. So now I can move on and do all of that again for the girls. Okay, so what does mu of g equal? Yep. And again, we do not know mu of g or sigma of g. We do know x bar of g, which is 64.3. S of g is 3.15. And my sample size was what, 45? Conditions again. Normal, 45, greater than or equal to 30. That's the CLE. are as stated. Independent. Okay. I'm tired of writing all of that. All right, so let's look at this. Since we know we are doing a 2-sample t interval for means. Do I need to wait a sec or sorry, just tell me if I'm getting. Sorry, I'll scroll. Okay, so I'm going to go ahead and write out my formula that I'm going to use. I'm going to use x bar of b minus x bar of g plus or minus t crit times s boys squared sample size of boys plus g squared over sample size of g. Let's look on your calculator here.
We have to do this every time.
What?
So do we have to write this down every time?
Yes. All right. Yep. Just get in the habit of doing it. Okay. What test do you think we might want to use on this one?
You
You got a stat and then test. Which one are we going to use? 2-sample t int, right? So you guys go ahead and find that 2-sample t int. We're doing the interval. Do we have individual data values or do we have statistics from our sample? We have statistics, okay. All right, so do you guys need me to pull the calculator screen up here or yes? Okay. All right, so we're gonna go stat, test. Okay, 2-sample t interval. All right, I don't want data. I want stats. Okay. Now, we decided to do boys minus girls. Could you have done girls minus boys? Yes, absolutely. You just have your interval would be negative instead of positive, okay? It's fine. You can do it either way. You just need to be clear with what you're doing. Okay, so my x bar for the first group, what do you think I'm going to put in? Yep, 66.9. What about S for the first group? 3.08, right? Sample size for the first group? 55. All right, that was all the stuff about the boys. Then for the girls, we were 64.3, 3.15, and my sample size was 45, right? Okay. We wanted a 95% confidence interval, right? This is where you can change that depending on what the question is asking you. We are not pooling right now. We're going to calculate. This is your interval at the top, okay? Raise your hand if you are not seeing this on your calculator, if I lost you somewhere along the way. Please ask if something's not going right. Yeah. So, so usually what the scoring guide says is has named or that way, because sometimes they will keep it like questions intact. They don't like just the answer being there. Right, because we did it all over here. Yeah. They don't want you to be like, stroke. Yeah, so, yeah. Okay. Yeah, so we're going to do all that. If you're like, don't write it wrong. Because if you write more things than you actually so it usually says name, my name, or
But then like here, we have to go on.
you don't have to fill it in. I mean, you could fill it all in, key it all into your calculator, and you get the same result, but that's really not really. All right, so we get this interval 1.35-ish, we'll say 1.36 to, what was it, like 3.84? Are we okay with that? Am I done? No, I need to write my conclusion. So, we are 95% confident that the true mean difference, okay, we used to just say that the true mean, now we're talking about difference of means, so we say that the true mean difference for heights or of heights of boys and girls that Langley falls between 1.36 inches and 3.84 inches. Okay, so we're 95% confident that the true difference of the average of heights there is somewhere between 1.36 and 3.84 inches. How do you feel about that? Okay. Lots of details. You can do it. Is any of this really any more difficult than what we did before? No, it's a lot of the same stuff. It's just take the time to write it all down. Okay. All right, let's look at C. Okay, based on our data from question 2, is there significant evidence that alpha equals 0.05 to suggest that the difference in heights between boys and girls at Langley is different than at Madison? What do you think we're doing here? Yeah, we're going to do a 2-sample t-test for means. Okay, guys, and all of this stuff we did over here with the conditions and all of the mu sub b, mu sub g, all of that. If this was a problem on its own, you would have to do all of that. I'm not going to make you rewrite all of that for this problem. It's the exact same stuff. Okay, so just know we're referencing that. If this was a problem on its own, you would have to do that. Everybody good with that? Yes? Okay. All right, so now we can actually just get to the hypothesis test. So since it's a hypothesis test, what do you think I need to write? Like a null and an alternative? Yes? Okay. All right, so the null that I'm thinking about here, it's saying we're testing if the difference at Langley is different than it was at Madison. What was the difference at Madison? We actually knew that. You guys see it from up above? It's 2, right? If we did, because we actually had the population of boys, population of girls, average of those distance, and it was 2, okay? So our null is that mu of boys minus mu of girls is equal to 2. And then the alternative, mu of boy minus mu of girl, do you think it's going to be less than, greater than, or not equal to? Not equal to. Why? It just says different, right? Different means not equal to 2. Okay? All right. The formula, if we were doing this, we'd be finding a t value, right? What's my formula? Can we find it? We know it. There's an X bar.
Yeah.
It's really long, right?
Yeah.
Yes. Is it this that you're looking at, X bar? And it'd be of boys minus X bar of girls minus mu of boys minus mu of girls all over big square root S of boys squared over n plus squared over n girls. We're actually going to key this one into your calculator, guys, like doing the t's here. So we know the X bar of boys and X bar of girls. Do you think that's the information from Langley or from Madison? Langley, yes. So that was the 66.9 minus 64.3. What about the mu of b minus mu of g? What is that? That's Madison. And how much was that? 2. Okay. All right, so the S, we're talking standard deviation of the sample. That's back to being from Langley, right? Okay. So that's 3.08 squared over, what, 55? Plus 3.15 squared over 45. Let's see, key it in and see what you get. I want you to actually try to key this into your calculator because it's a little ugly. Use your fraction shortcut key. That's alpha y equals, if you forgot where it is. So X bar, that is just the sample mean. S sub b is the sample standard deviation. Like you don't like signs. Okay. Now we have so help. Not really using stuff. Others, what was the difference in heights? You know, it's two inches. Langley, you just have to. Okay, let me write it up here. See if you got it.
That's a drum roll.
Did you get 0.957?
Yes. Ooh, get a bird, guys. First I got negative 38.86, so yeah.
Yeah, you knew that wasn't quite right. Okay, so what this means, since I found this t, what does that mean for the picture I'm going to draw? Have I standardized it? So this is 0, and I am saying I'm almost 1 standard deviation above. It was a not equal to, though, so aren't I also that distance below? Okay. How do you find the area, the shaded area? I can't use norm CDF because I don't have sigma, so what do I use? TCDF, okay? And pick either tail, I don't care what you do. I'll go negative infinity to negative 0.957.
So how do you put infinity in your calculator?
You can just do a whole bunch of 9s if you want to.
All right.
You can do
I'll just do
D,
negative
2D.
10,000. That's what I usually do.
Yeah, let's do TCDF. Oh, the exciting conclusion after one.
I got a bad argument.
You got a bad argument. Oh no. Okay, guys. We don't have too much left. Let's finish this. If you guys notice, when you do the TCDF on your calculator, it's not like norm CDF as far as what it asks you. Okay, it doesn't ask you for mu and sigma. Why doesn't it ask you for sigma? Because we don't know it, right? Okay, but it is a T, so it asks you for degrees of freedom. What are we going to use for our degrees of freedom in this one? 44, yes. Why are we using 44? Smaller of the two sample sizes, and then that n minus 1, okay? So we are using degrees of freedom of 44. That says DF, okay? And I think you get 0.17, something like that when you do this. Okay. Is that my entire p-value? Does that take into account both ends here? It only takes into account one, so what do I have to do with that value? Yeah, so we're really doing 2 times this, okay? So my p-value is actually, we'll say roughly 0.34. And it's not a P, it's a T. Sorry. All right. Same as what we were doing before with rejecting, failing to reject. What do you think we're going to do here? Okay, so since our C value of is greater than alpha of 0.05, what do? We fail to reject our null, our null hypothesis. There is not enough evidence. And guys, this is something I was noticing when grading your last test. A lot of you, instead of saying fail to reject, you were saying we accept the null. No. We are just failing to reject it. Okay, you have to use those words. And we're not proving anything. We're just talking about what the evidence suggests. Okay, so accept and prove should never be in your conclusion. All right. So there is not enough evidence to suggest that the mean difference in heights boys and girls at Langley is different okay, so should say is different than the mean difference in heights of boys and girls at JMHS. Let's see if no, nothing's happening. Okay, are you okay without me writing the rest of it? Anybody need me to repeat it? Okay. So let's see, is different than the mean difference in heights of boys and girls at JMHS. Okay. Questions on that one? We doing okay? Yeah.
Do you actually have to state that it's a 2-inch difference?
Nope. Because all we wanted to know was it different? We're not saying it is exactly 2 inches. We just don't have enough evidence to say that it's not 2 inches. Okay? And if you think back to the confidence interval we did 2 inches fall within our confidence interval? Wasn't it 1 point something to 3 point something? Yeah, so it makes sense then that we failed to reject this, right? Because that 2-inch difference was within our confidence interval. Okay? All right, one example left, guys. We just have the matched pairs t-test. We need, all right guys, you need your calculator again. All right, we are going to edit some lists. So in the first list here, we're going to put the pre-test scores, and in list 2, we're going to put the post-test scores. What we're doing here is Mr. Grossman wants to know if his teaching is actually helping students on their test. So he's giving a pre-test and a post-test to see if they improve and if we can decide that that's based on his teaching. Do you guys see how that's a matched pairs? We're talking about pre and post, before and after teaching. Okay. All right, so in list one, I'm putting 32, 21, 53, 27, 55, 10. These are some rough scores. 19, 26. Oops. Okay, then in list two, you're putting the post-test scores, and they need to be in the same order. 277, 96, 90. All right, everybody have them in? Okay, we want to actually find the difference between the pre and post-test scores. You don't have to sit here and actually go, okay, 82 minus 32 and write that down and put it in a list. Your calculator can do this for you. So go back to your main screen. Which list am I going to subtract? Like, what's the order of the list I'm going to do with my subtraction? Yeah, so we're going to do L2, which is second number 2, minus L1. And we want to store these new values in list 3. I'm going to do store in list 3. We're okay with that? Anybody having troubles with where store is or how to subtract? Please ask. Dave, are you good? Yeah. For sure?
Yeah.
Everybody okay with why we have to do L2 minus L1? Otherwise you're going to get negative. All right, so we now have our new values in L3. Store. Yeah, the little STO key on the left there. Okay. All right. So let's go back. Let's see if my smart notebook thing is writing for me. Just go to a blank one and start over. All right, guys, so on your sheet, you had the pre-test scores, you had the post-test scores, right? You had the list. We could, if we wanted, write out the difference, that delta in post minus pre, because you now have them. If you go into your edit list, your list 3 is all of those values. I'm going to write them down. I just want you to check to make sure these are the values that you have in your L3, or that showed up when you did the difference there. We're okay with that? Okay, so they tell us we're assuming the scores are normally distributed for both tests, and we have a random sample. What?
Isn't it 68, 50, and 30?
That should be 68, yeah. Thanks. 78 minus 10 is 68. Okay. I know, that's the tough stuff, right? All right, the question's asking us, is there significant evidence to suggest that Mr. Grossman's teaching improves the scores on this math test? So we're doing a hypothesis test, it's just a matched pairs test. So let's talk about mu of delta. This is the average change in test scores. And we did post minus pre. Okay, you're just defining what we're looking at. We need to write a null and an alternative. What do you think the null is? We're checking to see if this works, if there's any change from the post to the pre. So what do you think the null is? That it equals 0, that there's no change. Yeah, so mu of delta equals 0. That's my null. Alternative, we want to know if his teaching worked. So what do you think the alternative is going to be? Delta is greater than 0. Okay? Does that make sense? Okay. All right. Conditions. We got to check those, right? All right. SRS was stated. For normality, there's two things you could use for this. What do you think those two things are? Is the sample size big enough? No. Okay, so can't use sample size. What else could we use? Okay, you could look at your normal probability plot. So you could say NPP is approximately linear. If you look at it, hopefully you see that it is. What else could we do though? Yeah, it's just stated. Go with that. Normal, stated, okay? Just reminding you of all your options there. So you have to do one of those. Or stated, okay? All right. To actually do the hypothesis test, we need some info here. I need X bar of the change, I need S of the change, and I need sample size of the change. How might you go about finding those things? Something you haven't done for a while. Your calculator's going to do it. What'd you say?
The one variable.
Yeah, one variable statistics. So you're going to do one bar stat of what though? List 3. Yes. So you need to do one bar stat. So you don't have to write this down, just reminding you, one bar stat of L3, okay? Okay. So one bar stat of your list 3. All right, guys, what'd you get for X bar? 55.75, yes. What about S? And what's our sample size? 8, good. Okay with that? All right, it's a matched pairs t-test, right? We don't know sigma. So I need to find my t. Here's that formula. Looks a lot like what we did last week, and only there's a lot of deltas going on in there, okay? You've already found the difference, so you're not going to have the subtraction of two things going on. That's the difference here with matched pairs. So we are looking at our 55.75 minus, okay, what is mu of delta? 0. Yeah, that's what you're starting with in your null there. Over 8.35 over square root of 8. Key it in, see if you get what I get. Is everybody okay with the 0 in that? Okay. You're getting like 18.9. Without actually doing the TCDF, what do you think the t-value is going to be? We're saying this is like 18.9 standard deviations away from the mean. Is that real likely? No, so pretty much 0 for your t-value. Okay. Still make your little picture. We're doing where we standardize, 0's in the middle. 18.9 is like out here, so. So we'll make this teeny little part 18.9. You certainly can do the TCDF, and you'd be going from 18.9 to infinity. What are your degrees of freedom this time? 7. It's good to get in the habit of doing that over to the side here where you're listing all of the different pieces you're using to write down what degrees of freedom are. And you basically get 0. Are you guys seeing it with the to the negative whatever exponent? Okay. So what are we going to say with our conclusion? Since our t-value of 0 is what? Is less than alpha 0.05. We reject, yes, we reject the null. And I would say there is significant evidence to suggest what? What are we talking about?
The test score, the true test scores increased after Mr. Grossman's teaching.
Yes. So to suggest that, we could even say that student test grades improve, increase, however you want to say that. Again, it's back to making sure you have the context in there. I think you're getting much better at rejecting or failing to reject appropriately. Okay, guys, questions on anything? We'll stop there for today. We do have, I'll have some practice for you next time. We made it through that.